Because if I'm interested in two numbers that multiply up to positive 6, but add up to -5, -2 and -3 are my men. Colloquially speaking, of course. -2 and -3 are numbers, not men. All right. So, oh my gosh. All right, so. Let's through some examples run. No. Welcome back. We're going to look at another lesson. This time we are looking at lesson 11-2, rational expressions in your book, page 575. We're going to talk about the definition of a rational expression. I am not just randomly looking off to the side like a crazy person. I'm looking at the book, which is not the same as the camera. The camera is like right there. Oh my gosh. Right there. Yeah, so a rational expression, we said in the last lesson, we say r of x, where this is our rational expression, is defined as some p of x divided by some q of x, where both p and q are polynomials. In the future, you'll learn there are other kinds of rational expressions where your numerator and your denominator don't have to be polynomials, but it's a pretty good starting point. It's a pretty good definition to start with. There's just something we have to worry about. So, because this involves division, we have to be careful about our denominator. Because remember, you cannot divide by 0. If I had something like 0/10, that's fine. That's like asking, how many times does 10 go into 0? The answer is 0 times, right? Or, what's another way to put it? If I had 0 pieces of pizza and I needed to split them up between 10 people, I could do it for sure. It's just that nobody would get any pizza. There would be 0 pieces of pizza per person. But if, on the other hand, I asked you, well, what's 10 divided by 0? Although your, very developing human brains think, oh, I bet that's 0 too. I saw a 0. No, this doesn't make any sense. You can't ask how many times does 0 go into 10, or you can, but again, it doesn't make any sense. 0 zeros won't make a 10. 5 zeros won't make a 10. A billion zeros won't make a 10. No number of zeros are ever going to make a 10. So this scenario we call undefined. Remember, so we have to be very careful when we are looking at these rational expressions not to ever let our denominators equal 0. To do that, we have this new thing called excluded values. Excluded values are any values for the variable that would cause the denominator to be equal to 0. That is no good. And so we say the variable, whatever it is, can't equal that value. Let's jump right in and see one where that happens. So look at example 1, where we're just supposed to state the excluded value for each rational expression. So we have 5m minus 3 divided by m minus 6. Now, again, first of all, this is just an expression. We should be able to plug values in and just kind of see what happens. So we could even set up a little table here if we wanted, where we pick some value of m, and then we see what happens. What's 5m minus 3 over m minus 6 going to be equal to? For example, we could say, you know what? Let's find out what happens when m is -2. And so it would be 5 times -2 minus 3 over -2 minus 6, right? So we'd get -10 minus 3 over -8. We'd get -13 over -8, which ends up being the same thing as positive 1.625. Okay, so when m is -2, this whole expression is positive 1.625. What if we decided, you know what, let's find out when m is 0, right? 5 times whatever m is, divided by that minus 6. 5 times 0 is 0. 0 minus 3 is -3 over -6. Oh, it ends up equaling 0.5. Cool, right? Let's plug in 3. So 5 times 3 is 15 minus 3 over 3 minus 6. So we end up with 12 over negative 3. Oh, wow. Now the result of the ratio or the rational expression is negative, but it's negative 4. That's still fine, right? That's just a number. What if we plugged in 6, right? 5 times 6 is 30. 30 minus 3 we can definitely still do. Our numerator is going to be 27. But in the denominator, 6 minus 6 is 0. And how do we divide 0 into 27? How many zeros would make a 27? 0 of them? No, 0 zeros don't make 27. 100 zeros? No, 100 zeros don't make 27. A billion zeros? No, a billion zeros don't make 27. No number of zeros will make 27. This is why we break out the big guns and we say, oh man, that expression is undefined. But we don't like it when that happens. So we say, you know what? You know what I'm saying. M cannot equal 6. This is what we call an excluded value. Notice I don't care about the zeros of the numerator. I don't care what value would make the numerator equal to 0. That value in this case would be 3/5. If we were to plug in 3/5, we would get 5 times 3/5 minus 3 over 3/5 minus 6. 5 times 3/5 is 3. 3 minus 3 is 0. 3/5 minus 6 is negative 5.4. Not that it matters, because 0 divided by pretty much anything is just going to be 0. Again, 0 as a numerator is not a problem at all. So I don't care about 3/5 in the least. It's still a totally possible value for m. The one value that will not work in this case is 6, because it would cause the denominator to be equal to 0. Any value that will cause the denominator to be equal to 0 is no good, and we call that an excluded value. Let's take a look at part B, which gives us a new expression, x squared minus 5 divided by x squared minus 5x plus 6. First of all, one thing you'll notice is I haven't talked about canceling yet. One thing you might have been thinking up here is, well, wait, Mr. Raschuti, why didn't you just cancel the m's, maybe even cancel the 3 and the 6, and say, like, this is equal to 4 over 2 or something? Well, one thing I can say is it wasn't equal to 4 over 2, right? Literally none of the values we got back was just 2. All the values we got back depended on what m was, so nothing canceled. Later on we'll get into why this is, but the basic reason is there is no m in this expression. I know that's confusing because you think you see 2 m's, but you don't. What you see is m minus 6, the whole linear factor connected by those parentheses, and the whole linear factor, 5m minus 3. m minus 6 and 5m minus 3, although they do both have m, and they both have numbers, I guess, are not actually common factors. Nothing there cancels out. The same thing is going on here. Yes, I know, they both have an x squared. In fact, they even both have a 5. But if you wanted to get rid of those and say in some sense, oh, this is always like, I don't know, 1 over x plus 6, all you have to do is plug in a single x value, anything you want, and you see it's not going to equal the same thing. For example, let's say we said, let x equal 0. This would now be 0 squared minus 5 over 0 squared minus 5 times 0 plus 6, which is negative 5 over 6, right? Whereas this up here would just be 1 over 6. These two things are not the same, right? So you're just going to find whatever way you might want to cancel right now, it's not going to work, at least not without proper factoring. As far as the excluded value, though, which is our only job at the moment, we definitely want to do some proper factoring. For that numerator, nothing factors out. It's just going to stay x squared minus 5. But that denominator, you should remember, oh, that thing that we spent all that time on in chapter 7 and 8, it's coming back again. It's not going away. We can factor this expression as x minus 2, x minus 3, because if I'm interested in two numbers that multiply up to positive 6, but add up to negative 5, negative 2 and negative 3 are my men. Colloquially speaking, of course, negative 2 and negative 3 are numbers, not men. So once I write it this way, then I'm interested in what would cause a problem. And again, that means I'm interested in the zeros of my denominator. Just like we did earlier this year with zero product property, I ask myself, if x minus 2 is 0, what is x? X must be 2. But again, in this case, what I actually want is for x minus 2 not to be 0. And so the same thing is true here. I don't want x to equal 2. What about x minus 3, right? Where will x minus 3 be 0? Well, it would be at 3. But I don't want x minus 3 to be 0. So I don't want x to be 3. And these are what we call our excluded values. So what I would like you to do is to look at Check Your Progress 1A and 1B. You don't need to simplify anything. There's no canceling involved here. Just tell me, what should I not let x equal, because it would cause the denominator to be equal to 0, and that's bad. I have completed my work for Check Your Progress 1A and 1B. You can see on 1A, we have no plus or minuses, so it is simply 3 times x, which cannot be 0. You can see I'm essentially using like some sort of division property of inequality or something, but basically you're just obeying the same rules we've obeyed all year long. If we do something on one side, do it on the other, and do opposites, and that shows you, oh, so x cannot be 0 for Check Your Progress 1A. Again, notice at no point here am I doing anything with my numerators. All of these are my excluded values, right? On Check Your Progress 1B, we had a quadratic, and it was non-monic. So I definitely went to my box method. Of course, I knew where the 3x squared came from. Of course I knew where the minus 5 came from. Do my little table over here and figure out the two numbers I need that multiply up to a times c, not just c, negative 15, and add up to that middle term b, 14, are negative 1 and 15, and I factored it out to get 3x minus 1 and x plus 5 as my factors. I figured out 3x minus 1 would be 0, which is a problem, at 1/3, and x plus 5 would be 0 at negative 5. So again, excluded values, x cannot be 1/3, x cannot be negative 5. I have no idea why example 2 is in this lesson. Every year I get here and I just don't understand it. I don't know. Maybe it'll pop up in the homework and you need to go back and look at this. I just don't see a reason to do this. I don't know. I guess I'll run through check your progress number 2 real quick because you can read the example that they did. Okay, Kelly is going to lift a 535-pound rock. Good for you, Kelly. Using a 7-foot lever. So she places a fulcrum 2 feet from the rock. So here's a big rock. No, it's not a cloud. It's obviously a rock. And we're going to put a fulcrum right here. And we're going to put our lever all the way here. And we're going to try and push down with some amount of force to push up 535 pounds of rock. And we know that the distance here is 2 feet. So that's a 2-foot distance. And then the lever as a whole, so this whole distance here is 7, right? So what can we figure out? Well, we can figure out that this part right here must be 5 feet. And it says that our mechanical advantage is the length of the effort arm. That's where we're pushing. So that's this part right here. Length of the effort arm, which is 5, divided by the length of the resistance arm. So basically it ends up being a ratio between the different sizes on our lever, which kind of makes sense. If you imagine we placed it directly in the middle, we would have no mechanical advantage whatsoever. It's only if we start kind of shifting it away. If we made it longer, our job would be way harder. If you had just like just a little bitty bit to push on, your job is a lot harder. Now, it's not harder with this because this weighs like nothing, but a 535-pound rock, that's a little bit different. So we've got a 5-to-2 or a 2.5 whatever mechanical advantage. I don't think it has any units. So the force we're going to apply is going to get enhanced by a factor of 2.5, and we need that to equal enough to move 535 pounds of rock. So we're going to divide by 2.5 to isolate the force, and that means that F equals, I don't know, how many times does 25 go into 5,350? Goes in 207 times. So she needs to be able to place 207 pounds of force. Is that even right? I just made that up. I mean, not literally, of course. 535 divided by 2.5. Oh, I did get it wrong. Ah! So frustrating. Should I cut this part of the video out or should I leave it in? Cut it out. Everybody makes mistakes. Okay, so 214 pounds of force is what we have to apply. Not us, Kelly. She's the one trying to lift the rock. Example 3, we've actually done something like this before. We've just used our power rules to multiply stuff out or cancel stuff, right? Negative 3x squared times 4x to the 5th divided by 9x to the 6th. So we've got some factors that cancel, right? One way to do this, we could actually just multiply everything out. There must be 7 x's up there because x squared times x to the 5th, that's 7 x's. Negative 3 times 4 is 12. Of course, we have that same 9x to the 6th up there. Negative 12 is the same thing as negative 3 times 4. 9 is the same thing as 3 times 3. Maybe we should call this negative 1 times 3 times 4 times 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6. So what cancels here, right? Some 3's cancel. 1, 2, 3, 4, 5, 6 x's cancel. What's left over? Negative 1 times 4 times x divided by 3. Well, is there an easier way to get to negative 4x over 3? Yes, there is, right? So just take a look at our powers up top, 2 and 5. And again, we already said, oh, that's 7 x's. But remember that when we're dividing, we're supposed to subtract. So essentially what we end up with is x to the 2 plus 5 minus 6 power, which of course is x to the first. And then we can also cancel things like 3 goes into 9 3 times. And so really all we're left with at that point is the negative, the 4, the 3, and of course the x to the first that we already figured out. And so when we put those back, we get negative 4 on top, divide by 3 on bottom, and we don't normally write the x to the first, it's just x, and that is answer choice, which one is that? D. So they pulled the fraction to the front, but it looks basically the same. Take a moment and work out check your progress number 3. Simplify that expression. All right, there is my work for figuring out that check your progress number 3 simplifies down to f, 2b to the third divided by c. You can see the 16 over 8 cancels to the 2 on top, of course, because the 16 is in the numerator. C squared over c to the third, we always leave our c wherever the larger power is, so that's down here in the denominator. B to the fourth over b, again, we're going to leave our power wherever the larger one is, that's here in the numerator. But we do need to take away that 1b we canceled out. 4 on top, 1 on bottom leaves 3 on top in our numerator. So there's check your progress number 3. All right, one more example. Let's state the excluded values of an expression we can simplify. Okay, so just like the previous one where we were simplifying monomials, we can also simplify polynomials. We can cancel out common factors for polynomials. The first thing we have to do, though, is make sure we identify the excluded values. So look at something like this one, 3x minus 15. Now we can factor that. It's not super important that we do just yet, but I'll go ahead and do it anyway. I noticed that they have a 3 in common. So I pull the 3 out, and I get x minus 5 as the other factor. For our denominator, again, hopefully those rusty factoring skills are coming back to you, and you can see pretty easily here, oh, that's x minus 5 times x minus 2. Pause. Before you do anything else, don't look at the fact that you have an x minus 5 on both the top and bottom of this expression. Don't look at it. Stop it. Before we do anything with that, let's identify our excluded values. If x minus 5 is in our denominator, that means that x cannot be 5, because that would cause a problem. If x minus 2 is in our denominator, that means that x cannot be 2, because it would make the denominator equal to 0. Come back over here, right? 2 squared is 4. 7 times 4 is 14. 4 minus 14 plus 10 is 0. That's no good. We can't let the denominator be 0. So x is 5 and x is 2 must be excluded. These are what we call excluded values. Now that we've done that, come back to the expression and realize, oh, wow, those x minus 5s as a whole factor are the same top and bottom. So those we can get rid of. And that means that the simplified expression here is 3 over x minus 2, presuming you don't let x be 5 and you don't let x be 2. So again, please notice the excluded values are from the expression at the beginning of the process, not the end of the process. So we have to exclude that 5 as well, even though over here it doesn't look like there's going to be a problem with the 5, right? Seems like it would be just fine if we plugged 5 in. It would give us back 1, right? 3 over 5 minus 2 is 3 over 3 is 1. But that's not actually true, because we would have to plug the 5 in at the beginning and get the same result. And we wouldn't, because if we plugged the 5 in at the beginning, 5 squared is 25, minus 7 times 5, that's 35, plus 10, that would be 0. Letting x equal 5 is a bad idea, right? Okay, go ahead and try and do the same thing on Check Your Progress 4a and 4b. That means that you will factor, but you will identify excluded values before you cancel anything out. All right, there's my work for Check Your Progress 4A and 4B. I'm presuming that the next time I get to see you all, we might ask some questions like, isn't this just equal to negative 5 over 2 or 5 over negative 2 or negative 2.5 or whatever? And the answer is a big no, that doesn't end up working. I mean, just plug in 10, right? 15 over 8 clearly isn't the same thing as negative 2.5, but I'll answer those questions in class for you. That is lesson 11-2, getting our feet wet with simplifying rational expressions while also making sure to exclude any values that would cause a problem. The main problem we have to watch out for is what will cause our denominator to be equal to 0. Any value that would do that, we exclude, we get rid of. I hope that has been helpful to you. Make sure to like and comment below. What did I get wrong? Surely I made some mistake along the way. Please tell me what that was. I love hearing about my mistakes.